The molecular weight of an air-water vapor mixture varies with composition. The effect of this on air compressors is usually small and can be ignored. However, gas centrifugal compressors can operate over a wide range of molecular weights, making this variable significant. As an example of how to account for variation in molecular weight, we will consider a change in relative humidity at rated inlet temperature. On a given day, the atmospheric temperature is 90 degrees Fahrenheit, and the relative humidity is 100%. At a barometric pressure of 14.7 psi, the molecular weight of air is approximately 28.4 gram per mole, while at the rated condition, it is 28.7. Let's investigate how the molecular weight enters the head equation. The term R that you can see here is given by the following relationship. It is equal to 1545 divided by the gas molecular weight. Therefore, we can rewrite the head equation to include the molecular weight as seen here. Rearranging to solve for the term containing the pressure ratio will yield the following. This relationship implies that a change in molecular weight affects the pressure ratio. Therefore, for a change in molecular weight only, we can derive the following useful relationships. For the rated conditions and for the new conditions. Now, dividing the second equation by the first one will yield the following. Simplifying this new equation, as seen here, will give the following useful relationship. Here, the new pressure ratio is equal to the new unknown discharge pressure divided by the inlet pressure, which remains unchanged. Rearranging this equation will give the following in terms of the new discharge pressure. Now, substituting for the known values, we then have the following. So, as you can see here, the new discharge pressure is equal to 20.5 psi. From this, we can deduce that decreasing the molecular weight will decrease the discharge pressure of the compressor. Now, to investigate the effect of molecular weight on shaft horsepower, let's refer back to the shaft horsepower equation. As you can see here, shaft horsepower is directly proportional to molecular weight. Therefore, we can write the following relationship. So, as you can see here, a decrease in molecular weight will result in a decrease in the power requirement. Finally, the following figure illustrates the effects of system resistance on this analysis. Here, a reduction in molecular weight lowers the compressor performance curve. Point A is the rated operating point. In this example, we have assumed constant inlet volume flow and therefore calculated the discharge pressure at point C. If the compressor in this example operated with system resistance, it would search its new performance curve, so the dashed line, until it intersected system requirements. The result would be operation at point B as depicted here. Therefore, the inlet volume flow would be somewhat less than rated, and the discharge pressure would be slightly higher than calculated. For centrifugal air compressors, the variations in inlet compressibility and specific heat ratio are so slight that we can almost always ignore them when analyzing performance. However, for gases other than air, the changes in these parameters may be significant. The following figure shows the directional effect of a change in compressibility only, and in specific heat ratio only. The red curve indicates that a decrease in the inlet compressibility results in raising the compressor performance curve when inlet volume flow is plotted against discharge pressure. The green curve indicates that a decrease in the ratio of specific heats also results in raising the performance curve. Let's once again realize that our analysis is based on a given rotational speed. Therefore, each inlet volume flow is associated with one and only one head value. So, when your compressor performance curve takes the form head versus inlet volume flow as seen here, then the head curve will not change in any of the examples previously considered. Recall, the head produced by an impeller at a fixed speed and fixed inlet volume is a constant. Okay, we can now develop a general equation to determine the discharge pressure that results from a variation in any or all of the inlet conditions at rated inlet volume flow for constant rotational speed. Referring back to the equation we have seen in a previous video, we find that a similar approach would yield a general equation for changes in inlet conditions. If we assume that the ratio of specific heats and inlet volume flow are constant, the discharge pressure equation becomes as follows. Now, if the specific heats vary, the discharge pressure equation to be used is this one here. Notice that we have added another corrective ratio factor that you can see here to account for the variation in the specific heat ratio. However, in either case, whether the specific heats vary or not, the equation for shaft horsepower is the same, as depicted here. Now, keep in mind, since K, the specific heat ratio, does not vary in a significant way for different air-water vapor mixtures, we can consider it constant when dealing with centrifugal air compressors. The change in K, however, can be significant for other type of gases. Therefore, we will have to consider the effects of changing values of K. Let's consider the single-stage compressor as defined in the following figure. Our problem is to determine the discharge pressure and shaft horsepower at the rated inlet volume flow for a change in inlet conditions, as seen here. So, the new inlet pressure will be 14.2 instead of 14.5 psi, the new inlet temperature 40 degrees Fahrenheit instead of 90, and the new gas molecular weight 28.4 instead of 28.7. In this example, since the ratio of specific heats is a constant, we will use the following discharge pressure equation to solve for the discharge pressure. Substituting for the known values, we then have the following. As you can see here, starting from the rated conditions and using the discharge pressure equation and based on the new inlet conditions, you can see that the new discharge pressure is 20.8 psi, so slightly higher than the rated discharge pressure of 20.6 psi. To calculate now the effect on the power requirement, we will use the following equation. Substituting for the known values, we then have the following. So as you can see here, the new inlet conditions resulted in a higher power requirement. Of course, keep in mind when necessary we will use the system resistance curve to make the proper adjustments. Sometimes it is necessary to consider constant weight flow. We can use the performance curve to predict discharge pressure and shaft horsepower for this case. Changing the inlet conditions will affect the inlet volume flow. Because we are dealing with variable inlet volume flow, the head produced by the impeller will also vary, as seen here. In this video, we will use the compressor defined by the following figure and predict the discharge pressure for a change in both the inlet temperature and inlet pressure. Let's consider a change in the inlet temperature to 100 degrees Fahrenheit and inlet pressure to 14 psi. Here, in this example, molecular weight, ratio of specific heats, and gas inlet compressibility will remain at rated values. The volume flow equation that you can see here implies that for a constant weight flow process, the inlet volume flow is directly proportional to the inlet temperature and inversely proportional to the inlet pressure. Therefore, we can write the following useful relationship. Now, substituting for the known value, we then have the following. So, the new inlet volume flow is equal to 44,500 cubic feet per minute. So, basically here, using the compressor performance curve, we find that at the rated inlet volume flow of 42,200 cubic feet per minute, the head produced is 11,000 feet, and the head produced at the new flow of 44,500 cubic feet per minute is 10,900 feet. From the head equation that you can see here, we can establish that the expression containing the rated pressure ratio is directly proportional to the adiabatic head and inversely proportional to the inlet temperature. Therefore, for the rated condition, we can write the following expression. And for the new inlet conditions, we can write the following. Now, dividing the second equation by the first equation will yield the following useful relationship in terms of pressure. Substituting for the known values, we can then calculate the new discharge pressure. In our case, it is equal to 19.7 psi. Shaft horsepower for rated inlet conditions at a flow of 44,500 cubic feet per minute can also be determined from the performance curve of the compressor. As you can see here, it is equal to 1,410 horsepower. Centrifugal compressor performance varies with the rotational speed. For a given inlet volume flow, a higher rotational speed will raise the performance curve, as depicted here. If the variation in speed is not too large, say 90% to 105% of rated speed, we can predict the compressor performance from the fan law relationships. These state that the adiabatic head varies as the square of the speed, and the inlet volume flow varies directly as the speed. So, if we use the rated points as reference, we can write the following useful relationships. As you can see here, the new head is equal to the rated head times the ratio new RPM to rated RPM raised to the power 2. And for the volume flow, the new flow is equal to the rated flow times the ratio new RPM to rated RPM. From these equations, we can predict the speed required to overcome the effects of changes in inlet conditions. The methodology that will be outlined can be used for any variations in inlet conditions and for any type of performance curve. Let's consider our previous example involving a change in the inlet pressure only. Here, the drop in inlet pressure caused the discharge pressure to decrease from 20.6 psi to 20.2 psi. The question is, what speed is needed to raise the discharge pressure to the rated value of 20.6 psi at rated inlet volume conditions? The pressure ratio at rated speed for the inlet conditions under consideration is determined from the procedure previously developed. For this example, it is equal to 20.2, the new discharge pressure, divided by 14.2, the new inlet pressure. This is equal to 1.42. On the other hand, the required pressure ratio is equal to 20.6 divided by 14.2. Why is that? Because 20.6 is the discharge pressure that we want to achieve. 14.2 is the new inlet pressure. This required pressure ratio is equal to 1.45. Now, referring back to the head equation, we can see that for any given set of inlet conditions, the head is directly proportional to the term including the pressure ratio, as you can see here. And since the head varies as the square of the speed, according to the fan law relationship, then we can write the following. The term including the pressure ratio also varies as the square of the speed. From this, we can derive the following rotational speed equation. Now, substituting for the known values, we then have the following. So, the required speed or the needed speed to raise the discharge pressure to the rated value of 20.6 psi at rated inlet volume conditions is equal to 4,490 rpm. Notice here that we need to increase the speed from 4,350, which is the rated speed, to 4,490 rpm to accomplish the same discharge pressure. Now, at 4,490 rpm, the compressor will produce the required head. However, the increase in speed will also affect the volume flow, according to the fan law relationship. Here, for instance, the new flow will become equal to 43,560 cubic feet per minute, versus the rated inlet volume flow of 42,200 cubic feet per minute. So, the reduction of the flow to rated conditions at the new speed of 4,490 rpm would result in too much head. To better illustrate this concept, let's refer back to the compressor performance curve to see the effect on inlet volume flow and head for an increase in rotational speed. The solid curve that you can see here represents rated conditions. Point A is the rated operation point. Also plotted in this figure is the line for the fan law. Following this line to 4,490 rpm shows a shift in performance to point B, which represents the desired compressor head. Reducing the inlet volume flow to rated conditions results in performance at point C, as depicted here. To finish off this section, with these useful procedures, you should be able to accurately predict the performance for any single-stage centrifugal compressor. Furthermore, you should be able to analyze plant air centrifugal compressors by applying these techniques to each stage between coolers. The use of these techniques on centrifugal units having several impellers between cooling points will yield useful qualitative results. However, keep in mind, accuracy of the results will deteriorate in proportion to the number of impellers between coolers and differences in the molecular weights of the gases involved.